In this paper, to improve the anatomical consistency in medical segmentation, we aim to improve a recent method called connectivity modeling. We started from studying the feature space of a vanilla connectivity-based model. And we observed that two types of features exist in the entire feature space, which are the categorical features and the directional features. In the previous connectivity-based methods, these two features are highly coupled. In this work, we point that decoupling these two subspaces from the shared latent space can enhance the overall feature representation. According to that, we propose a novel directional connectivity-based model called DCONNet. We did our experiments on 3 public medical dataset and achieved SOTA results compared to all baselines. Maintaining anatomical consistency in medical segmentation is important, as minor geometric errors may change the global topology and cause functional mistakes in decision-making. A typical segmentation network models the problem as a pixel-wise classification task and uses a segmentation mask as the only label. Yet, this pixel-wise modeling scheme is suboptimal and may result in low spatial coherence in their prediction and lead to topological issues in medical data. This was improved by a recent method, called connectivity modeling. This method highlights the topological aspects of the segmentation problem with an interpixel relation-aware label called a connectivity mask. The connectivity mask, as shown here, is defined as a multi-channel mask with each channel representing if a pixel on the original image belongs to the same class with one of its neighboring pixels at a specific direction. By using this as the training label, we changed the problem modeling of the network from a pixel-wise classification to an interpixel connectivity prediction. There are 2 types of features in the latent space of a connectivity model. The first type is the categorical feature, which is directly reflected by the pixel connectivity of each entry. The second type of feature is the directional feature, explained as the direction of connectivity, which is mainly stored among the channels. Each of these 2 features forms a specific sublatent space. In previous studies, people built a connectivity-based method by directly replacing the training label with the connectivity masks. Therefore, these 2 groups of features were learned simultaneously through a shared network path, which may result in highly coupled latent space and introduce redundancy. In this paper, we propose that disentangling these 2 sublatent space help account for the dependencies and independencies between features. Based on this, we propose a pipeline to disentangle the directional subspace from the shared latent space and utilize it to enhance the overall data representation, as shown in the right figure. This pipeline is implemented by a novel network, called DCONNet. DCONNet has an encoder-decoder structure and several important modules. The SDE module is used for feature disentangling, the IFD module is used for directional-based feature enhancement and a size density loss that alleviates the common data imbalance problem in medical datasets. In a connectivity mask, different channels represent different directions of the pixel connection. Thus, as the network goes deeper, it naturally stores directional information among channels. Based on this observation, the directional features can be captured and manipulated through channel-wise operations. In SDE, we first extract a distinctive directional embedding called directional prior by coarsely supervising the intermediate features and squeezing the channels of the intermediate output feature map. Then, we channel-wisely slice both the prior and the latent feature map to form several subpaths and enhance the feature map via a dual attention module in each subpath. In directional prior, each channel represents distinctive directional information. However, in the original feature map, heavy categorical redundancy exists. Due to these different channel-wise redundancy levels of categorical features and direction features, the slicing operation caused an imbalanced dividing of these 2 types of features. Inside each subpath, the network learns how to focus on the dominant categorical information. Between the subpaths, the network learns different distinctive directional information. Then, after we stack these slices back, the direction information will be naturally disentangled from the original latent space and embedded into the channels. To ensure that the directional information can be effectively fused into feature maps in each layer, we further propose the IFD, which has 2 top-down dynamically interactive flows, the space flow and feature flow. In space flow, we enhance the feature map with the directional embedding we get from the last layer via a self-attention operation and generate a new directional embedding using channel-wise squeezing. In feature flow, we simply pass the enhanced feature map to a decoder layer. This design is mutually beneficial for both flows. The directional embedding fuses the directional information into the feature map in the feature flow. On the other hand, the feature map refines the directional representation by adding supplementary directional information at a higher resolution to the space flow. For our problem modeling part, we use the connectivity mask as the training label, and all other modules are kept from the original connectivity modeling method. We also proposed a loss function based on label size distribution, called size density loss, to deal with the two-level imbalance data in medical segmentation. We first sample the entire dataset and get the probability density function of the label size for different classes. We use the inverse logarithm of the PDF as an initial weight for each class, and we combine this weight with the dice loss, which gives the final size density loss. We did our experiments on 3 public medical datasets. The first one is our main dataset, called Retouch. It is an OCT retinal fluid segmentation dataset. The 3 colors in the visualization represent 3 kinds of retinal fluids. From the table, we can see DCONNet performs better than any baselines under any metrics while achieving the fastest inference speed. From the visualization, DCONNet made the most anatomically consistent prediction while others made topological issues in their predictions. The second dataset we used is the skin lesion dataset ISAC 2018. Similar results can be found both in the table and the visualization. Last, we tested our model on a topologically sensitive dataset, the Chase DB1 retinal vessel segmentation dataset. Again, our model did the best work on all metrics, especially the topology-based metric CL-DICE, and gave the best visualization result. Here is the overall results of the ablation study on different components of DCONNet on Retouch dataset. Here we demonstrate the effectiveness of the proposed directional prior and the subpath attention mechanism. From the left table, we can see that by using the directional prior and replacing the plain dual attention module with a subpath attention module, the result got improved. The figure on the right gives another aspect of how the channel-wise feature embeddings were getting decoupled through the proposed SDE. In conclusion, in this paper we proposed a directional connectivity modeling scheme for segmentation that decouples, tracks, and utilizes the directional information across the network, and we showed its effectiveness with various experiments on public datasets. Given the relatively small parameter increase introduced by this model, a future direction will be 3D segmentation. Thank you.